Linear systems are systems that satisfy superposition and homogeneity. In other words, if the inputs are A and B, then the output is FA plus FB. If the input is amplified by the factor of K, the output is also amplified by a factor of K. These properties means that the system's behavior is highly structured and predictable, allowing complex input to become decomposed into simple components and analyzed separately before the effects are combined. Due to these predictable, decomposable, and composable properties, linear systems have found wide application in science and engineering. Signal processing and communication. Signals, after passing through a linear system, can be decomposed into multi-frequency components and reconstruct. This is foundation of the Fourier transform. Circuit analysis. In most circuits, the RLC components follow linear differential equations. This can be solved using the superposition principle, frequency domain, and analyze, and Laplace transform. In traditional circuits, resistance R, inductance L, and capacitance C all satisfy linear transformation. These three equations are all in linear differential equations. Superposition principle. In linear circuits, multiple source circuits can be analyzed individually, and the result can be added together. Solving for each source independently would be extremely complex, but linear systems simplify this process. This graph shows a clear step of using the linear system to solve and simplify a circuit. Communication system include 4G or 5G, the Wi-Fi and Bluetooth. They all rely on linear system. Modulation and demodulation. The transmitting and modulation the signal. The receiving and recovers the signal using linear filters, MEC filters. Channel modeling. Wireless channel imply the linear superposition of multipaths. Therefore, multipath phenomena can be perfectly described using the linear system. This graph shows the step of modulation and demodulation in community system. Power electronics. Regulate switching power supplies and PWM control circuits, all through ultimately composed of a nonlinear device, can be analyzed using linear system after linearization. Small signal modeling. Engineers linearize nonlinear circuits around a certain operation point. Delta y equal to A plus delta x. Using linear system tools such as Bode plots, gain matrix, phasor matrix, and stability analysis make power supply control scientific and designable.
Next, I will explain how linear systems are used in mechanical engineering. Mechanical engineering deals with structures, vibration control, and motion analysis because linear systems follow the rules of superposition and homogeneity. They help engineers handle complex mechanical problems in a simple and effective way. In this part, I will focus on two major applications: vibration analysis and model analysis. First, let's look at the basic model we often use in mechanical engineering. Many mechanical structures, such as bridges, car suspensions, and building frames, can be described by the linear second-order differential equation mx plus cx plus kx equals ft. Here m is mass, c is damping, k is stiffness, ft is the external force, and x is the displacement. The first major application is vibration analysis. Vibrations appear everywhere in mechanical engineering. The bumps when a car is driving, the shaking of a bridge under traffic, or the movement of buildings during earthquakes. The linear system model helps us predict and control these vibrations. For example, in a car suspension system, bumps on the road create the external force Ft. The spring provides stiffness K, and the shock absorber provides damping C. By adjusting these parameters, engineers make sure the car can absorb impacts from the road and reduce shaking so that the ride is both safe and comfortable. In earthquake engineering, buildings are also modeled as linear systems. Engineers use the equation to simulate how a building reacts to seismic waves. Based on the analysis, they can adjust the stiffness and damping of the structure to improve its earthquake resistance. The second major application is model analysis. Complex structures, such as aircraft wings or large machines, do not vibrate as a whole. They vibrate through many independent modes. Each mode has its own natural frequency and mode shape. Model analysis uses the linearity of the system to break down a complicated vibration into these simple modes. This helps engineers identify dangerous frequencies. For example, in bridge design, if one natural frequency of the bridge is close to the vibration frequency produced by vehicles, resonance may occur. Resonance can greatly increase the vibration amplitude and damage the structure. So engineers use model analysis to adjust the design and avoid the risk. Also, in aircraft engine blades, you can see in this picture, model analysis is also essential. Blades rotate at high speed and experience strong airflow forces. Engineers ensure that the natural frequencies of the blades stay far away from the excitation frequency of the airflow, preventing dangerous resonance and protecting flight safety. In summary, linear systems simplify mechanical engineering problems by using superposition and homogeneity. Whether we are calculating vibration responses or identifying natural modes, linear systems give engineers accurate and efficient tools. They play a key role in improving the safety and the performance of cars, bridges, buildings, and aerospace structures. That concludes my section on mechanical engineering. Thank you.
Application of linear systems in civil engineering. Besides electrical engineering, linear systems are also widely used in civil engineering, especially in structural analysis. In civil engineering, engineers often need to analyze structures such as bridges and trusses that are also subjected to multiple external loads. To ensure safety and ability, these structures must satisfy equilibrium conditions, which naturally lead to system of linear equations. Civil engineering structure problem. In a typical civil engineering problem, a structure may be acted upon by several external loads. These loads create internal forces and the reaction force at the supports, which are usually unknown. Engineers must determine these unknown forces to make sure that the structure will not fail under loading. For equilibrium conditions is a key idea. In civil engineering, structures at rest must satisfy the conditions of static equilibrium. This means that the sum of forces in the horizontal direction must be zero, and the sum of forces in the vertical direction must also be zero. Each equilibrium condition forms a linear equations, and each unknown force represents a variable. Linear system representation. When a structure has multiple joints or members, there will be several unknown forces. By applying equilibrium conditions at each joint, engineers can obtain multiple linear equations. These equations can be written in matrix form and solved efficiently using linear algebra techniques. Comparison and conclusion. Electrical engineering, the unknown variable are using currents. In civil engineering, the unknown variables are forces. However, both problems are solved using the same mathematical framework of linear systems. This shows that linear systems provide a unified and a powerful tool for solving different engineering problems and play a crucial role in designing safe and stable civil engineering structures.